Our next brief video is going to examine some of the review exercises for Chapter 14. You probably recall we just looked at the addition rule and the frequently asked questions about probability portions of the chapter, and will accordingly look at just applicable review exercises. In our first exercise, a pair of dice are thrown. First, let's find the chance that both dice show 3 spots. Here we go. So remember, the first thing to think about is, are the dice independent? Yes, dice always function independently, much to the chagrin of craps players. So the chance of each dice showing 3 spots is the 1 out of 6. So we can take the 1 out of 6 chance and then, since these events are independent, we can multiply the probabilities, and it's 1 out of 6 times 1 out of 6. To think of it in our other notation, it'd be 1 out of 6 to the power of 2, because there's 2 trials. It doesn't matter that the 2 dice are thrown at the same time. Remember, dice are completely independent. And the chance would be 1 out of 36. For part B, we've got a somewhat different scenario. We need to find the chance that both dice show the same number of spots. We can imagine that one of the dice is white and the other is black. And to help you frame this, no matter how the white one lands, the black one has a 1 in 6 chance to match it. So the chance that both dice show the same number of spots is always going to be, oops, there should be, yep. This figure spells it out more nicely than my mapping it out for us. So let's just look at this and go back. You can see that there are 36 total ways for the dice to fall, and all these ways for the dice to fall are equally likely. Now, how many times do the numbers on the 2 dice match each other? Well, that scenario goes right through the symmetry line here of the die. So we've got 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. 6 possible combinations out of 36 lead to the 2 dice falling on the same number. Let's think about another dice problem. In the game of Monopoly, a player rolls 2 dice, counts the total number of spots, and moves that many squares. The chance that the player moves 11 squares, no more or no less, is going to be equal to the chance of getting 11 in some combination of the die. And so we can think there are different ways that we could roll 11. We could get 5 out of 6, 5 on our white dice, or 6 on our black dice, but we could also get them on the opposite die. So our white die could be 6 and our black die could be 5. So there are only 2 out of 36 total possible outcomes when you're rolling 2 die. So there's a 2 out of 36 chance of getting 11 squares. Note that there's no other ways to get 11 from these two die. Now we have two true and false questions. First, if a die is rolled 3 times, the chance of getting at least one ace is 1 out of 6 plus 1 out of 6 plus 1 out of 6. There should be some alarm bells going off in your head at this point, because we remember that the addition rule requires that the events are mutually exclusive, but these are independent events. So you can't add the chances. You would instead, to get the chance of rolling at least one ace, you would multiply instead. Next, let's consider if a coin is tossed twice, the chance of getting at least one head is 100%. This should lead to alarm bells as well, because remember, every toss of the coin is an independent event. So you could very easily get a head 2 times in a row, or 2 times in a row, or tails twice in a row, because the probability of getting, let's look at just heads, probability of heads is 1 out of 2 for every single roll. So the chance of getting at least one head on your 2 rolls is 1 out of 2 times 1 out of 2, or one out of 4. Oops. We're just going to look at a couple more problems. In our next problem, we have 2 cards that will be dealt off of the top of a well-shuffled deck. You have a choice to win $1 if at least one of the 2 cards is a queen, or to win $1 if the first is a queen. Which of these options is better? Well, are they equivalent? No. These options can't be equivalent, because in the first one, there are more ways to win. You could win on the first card, or you could win on the second card. Just at least one of the 2 cards needs to be a queen. In option 2, you just have one opportunity to win. The probability that the first card is a queen. So option 1 is better. If the chance of A is 1/3, the chance of B is 1 out of 10, or 1/10. True or false? And explain. If A and B are independent, they must also be mutually exclusive. This is false. A and B can happen together, and the chance that A and B happen together is 1 out of 3 times 1 out of 10. So they aren't mutually exclusive. Just because they are independent, that does not give us any indication about whether they're mutually exclusive. or it doesn't, require that they be mutually exclusive. For scenario B, if A and B are mutually exclusive, they cannot be independent. This is also false. The same reason here. The probability of A and B is still 1/3 the probability of A times the probability of B. We know that they are mutually exclusive, so we know the probability isn't the same. If they are mutually exclusive, we would, of course, add the probabilities because the addition rule specifically applies to our mutually exclusive events. So I misread my notes for a moment. But the real point here, it doesn't have to do at all with the actual probability of the two events happening together, but whether or not mutually exclusive events cannot be independent. And this is false. Events could be mutually exclusive and be still independent events. And we're going to look at just one more problem. One event has a chance 1 out of 2, and another has a chance 1 out of 3. Let's fill in the blanks using one phrase from each pair below to make up 2 sentences that are true, and these are our options. Here's our first sentence. If you want to find the chance that blank will happen, check to see if they are. So if you want to find the chance that at least one of the 2 events or both events will happen. So we need to make 2 true sentences here. This is a little bit of a logic problem. So let's start out with just choosing, we'll say, if you want to find the chance that at least one of 2 events will happen, check to see. So in our first scenario, we've got at least one of 2 events will happen. Check to see if they are mutually exclusive. If so, you can add the chances. And the converse sentence would also be true. So if you want to find the chance that, so in the second version of the sentence, if you want to find the chance that both, I guess I can't switch colors. If you want to find the chance that both events, we use a dashed line here, that both events will happen, check to see if they are independent. If so, you can multiply the chances. And we're only going to cover problems 1 through 6 from this chapter. The rest don't really apply to contexts that we need to be aware of for the material we're covering through the rest of the course. In terms of applying some of the ideas from this chapter to your studying for the upcoming exam, I would highlight thinking about like item 6. You should certainly make a lot of sense to you. Understanding an item like number 4 to pick the right prediction of which option is better. And true or false questions like we see in number 3, where you need to remember that the die each roll as an independent event, or discriminating between an independent or mutually exclusive events, and figuring out, these basic ideas of the chance of showing particular dice patterns. We're not going to do anything too sophisticated with that, but you should be comfortable with these few applications. Good luck, and may the odds be ever in your favor.